Hi everyone, welcome to the Game Engine Development Meetup. We're very happy to see such a large crowd come and join us, and especially for special thanks to Anton and Thomas for coming and sharing your insights. That was very interesting, thank you. So many of you are game developers, and maybe you're pretty far along your prototyping for a particular game. So perhaps you've got, you're coming from the, Western Sydney University and you've got city simulation already sort of going. So you've got an idea for what the gameplay should look like, what narrative it's telling, what the core mechanics are going to be. It's a multiplayer game, so there needs to be some sort of magical glue to connect the players together, and they're each going to be playing on their own devices. So game servers are that glue. They are what sustain the illusion that players on different machines, in different locations, are collectively experiencing a common game experience. So very often when you're talking about game engines, it's usually something that's a bit of an afterthought. After the problems to do with game design, with content creation, with rendering, you sort of think, oh, okay, I should probably connect these together over the network somehow. So, should you build your own server solution? That's one option. Or should you use something off the shelf? There can be a lot of hype and marketing spin out there for the off-the-shelf products. So it's important to sort of be able to give a good criticism or evaluate critically what the features are and sort of compare it across the solution space. It's an important decision for a multiplayer game because it really has significant ramifications for the development and the operation for your game. So I'm here to talk to you about a useful kind of lens which you can sort of use to better compare and contrast the various offerings out there. And with this lens, it should be possible for you to make a better judgment on what kind of game server solution to use, or give you ideas for what kind of game solutions that you may want to, server solution that you may want to build yourself. So, welcome everyone. A little bit about me. I'm a software engineer here at Wargaming Sydney. I've been here for a little while. Wargaming Sydney is part of a larger organisation. Of course, Wargaming is famous for making World of Tanks. There are also other combat-based, arena-based combat games like World of Warships, World of Warplanes. So all of these titles and other titles in the past from other companies, they run a game server engine called BigWorld. That's part of a BigWorld server, part of a bigger offering known as BigWorld Tech, and this is an engine that was developed here in Sydney. So let's start by defining some terms that describe what fundamentally every game server does. In any game, there is this concept of game state. If you think of any game being a simulation, especially as coming from AI space, simulations are quite in the forefront. Then the game state is really the state of play at any particular point in time, and that evolves over the time steps of your simulation. So it's really the positions of the players in the first-person shooter, for example, their health, what color they are, whose turn it is, what map they're playing in, the state of any mutable objects in that map. In chess, it's got to be the grid positions of all the pieces, what color they are, and whose turn it is. So in some sense, there had to be some description of that game state present at any given time, how the game state is defined for a game server. During simulation, game rules and player actions come together to change the state of the game to a new state. And so there has to be some way for the gameplay programmer to be able to manipulate how that game state changes. Once you have a new game state, of course, you then need to synchronize to the bits that need to know about it. So for players, certainly, but there might be other things like server-side processes that do some sort of analytic processing on them. Especially in the case of AI, that might be an off simulation process that you might want to scale up. So could be very useful to think about it in those terms. Can everyone hear me? Okay, cool. So, what exactly do I mean by game state? Let's break it down a little bit. In every game, there are actors that exist in the game. They're sort of the significant things in your game. You count among the actors the players of the game. They run around, they can do stuff to each other, like shooting each other, trading, healing, communicating, fishing, making pots, so on. But actors in the game today aren't just the players. They're also other players are generally not the only things that players can interact with. So things like vehicles, things like power-ups, things like items. Players might throw grenades, so they might be actors. They might drive vehicles, so that's especially important if you're making a tank game. So actors in the game state also include non-player things that players interact with, and that's pretty significant. And the significant parts of those are the ones that you want to deal with in your game state. So we have different types of actors, but actors of the same type generally have different data. So they have positions in space, they have name, they have a clan affiliation, they have health, they have weapons that they're carrying, they have inventory. So there's data associated with each of those actors. In addition, there's usually some sort of interaction mechanism between the actors, so some sort of event system or some sort of message passing system. So players fire weapons, they jump, they move, they communicate, those kinds of things. Significant events that happen in gameplay, they often involve or reference the actors and their data. So you can kind of think of gameplay for all games as being described in these terms. So game server engines need a way for a game designer or a game programmer to tell it what the allowable game state space is. So it needs to be able to represent game state in memory so simulation logic can run on it and it can manipulate it. It also needs to be able to serialize parts of that over the wire for synchronization. So for a given game design, a game programmer's job is to translate the game state that comes out of the game design into a more formalized data model that a game server engine can then use to manage in memory. So there needs to be a way of mapping those actors, the data, the interactions from that game state and the game design into actual data and logic objects in the language used by the game server engine. So for example, you might have your actors be different object classes, data would be member data on those classes, interactions could be member methods on those classes, and that's a pretty fairly common way of mapping game state into a data model that's used by a game server engine. In a lot of game server engines, players are usually treated specially compared to non-player actors. This is because they have the connections to the end users, so there needs to be a way of transporting the player inputs from their device to the simulation. And so they're often represented slightly differently to non-player actors. As an example, you see this in Unreal Engine, for example. You'll have a class of actors called pawns. They're controllable by another class called a player controller that represents the human will according to the docs. The extent to which players are special is something to sort of look at. A lot of game server engines pile a lot of the functionality for their game engine into the player class, and this can have a bit of a significant effect on how complex your implementation of the player becomes. So it just means you have this sort of big monolithic classes for your player, and that can be not so good from a software engineering point of view. As well as players being special, often there's the game simulation itself being represented in some way as an actor. This kind of actor usually holds data that's considered to be global, or data pertaining to the arena that you're playing in, as well as interactions with the arena or the environment also sort of specified in terms of that. So for a given game engine, it's interesting to see whether there's a unified layer that sort of ties the actors, whether the player actors sort of treated any differently, what sort of simulation level actors there are, and what happens with non-player actors. So it can be quite different. All the various types of data models that game server engines have to represent game state. You can actually talk about the different types of meta models that game server engines use. So I'm clearly making up a term here, so you'll have to forgive me. Roughly speaking, we can talk about 3 levels of data meta model. So let's start with player-centric. This is where the only actors that the game cares about are the players, and all the data interactions are solely in terms of the players. For example, my player has health. Simulation has decided that I was shot, so my health integer goes down. So I might have health integer data member on my player. Later on, Joe wants to trade his awesome shield for my awesome spear, so there's a trade transaction that's being facilitated using events over some messaging model. So that's kind of the flavor of what you'd expect. Game engines like GameSparks and PlayFab, they're good examples of this. They're really focused around getting functionality around players, so things like matchmaking, things like leaderboards, they kind of supplied as part of that. So it's all about the players. It's a good corporate mantra, but it can be quite limiting once you get to the point where you actually need to represent non-player actors in any sort of significant way. It can be a bit unwieldy in a player-centric model to sort of push that functionality into the player functionality. So really what you want is some way of expressing a non-player entity in some form, as well as player entities. So the next type of model is the entity-centric model, or actor-centric model, if you like. This is sort of the kind of model that sort of Unreal and Unity sort of have, although component-centric is also something that they fall under. But the idea is there's different types of actors often have a lot of shared functionality between them. And you can, while prototyping, it's really tempting to have your actors type implementation and then just copy it over to a new actors type and then sort of tweak some things. So that orc guard that you made for the Lord of the Rings online so many years ago, it needs to be tweaked into a Stormtrooper for a Star Wars game, perhaps. And it kind of works the same way, except for the part that makes it fire a blaster that shoots in a straight line rather than a crossbow that shoots a parabolic projectile. And this other thing that makes the combat sort of work differently because it's Stormtrooper, not an orc. But there are other things that we want to keep, like the pathfinding and so on. Totally not based on a real-life example at all. It's very easy for the original design integrity to be a casualty once you start cherry-picking these features. So what you really want is something where the functionality is implemented at a more granular level. And this is what we have with component-centric architectures. Essentially, we have actors and they hold components. And they're sort of independent pieces of functionality and data, actors that sort of serve as containers for these components. You see this in game engines, like Unity and Unreal sort of are really good examples of this. So the functionality that a component supplies is very focused. In a lot of component-centric engines, there'll often be something like a position rotation component, and it's expected that actors will have, with that component, will have some sort of representation in 3D space. There might be a collision component, which holds a collision mesh that's added to the collision scene. So game designers specify the actors in a game in terms of these components. Some game engines, actors are just containers. The actors themselves don't implement any significant game logic or have any sort of game engine functionality. All they're doing is just holding placeholders for the components. The type of data model that a game server engine can support is really pivotal to what the gameplay programmers are going to have to spend their working lives having to deal with, and how much they're going to have to spend building their own infrastructure to keep track of the game state compared to building up game-specific logic that handles data and interactions on that game state. The extent to which non-technical gameplay designers can build the data model is also pretty important. Kind of nice to have visual scripting and that kind of thing that you see in sort of Unreal Editor and so on. So if an engine can sort of support easy prototyping without any programming knowledge, this can be quite appealing for prototyping, as long as it also allows you to sort of open the hood and for gameplay programmers to be able to implement the sort of game logic that they need to efficiently and performantly. So with a particular type of data meta model that a game server engine supports, it's important to sort of evaluate on the basis of what kind of API it supports and what kind of language, and what kind of languages, rather. So I'm going to talk a little bit about that. I'm going to talk about what kind of data types to expect, what the significance of the API is if it's between the client and the server. That might be different. So it's really important that the API sort of be really easily understandable, and so good documentation and supporting materials are really important. Simulation API to modify data model is usually associated with the language or perhaps a set of languages. So a good question to ask is what languages are supported. Dynamic languages are useful for rapid prototyping due to avoiding long compile cycles, so you can get those short iterative loops. Lua, JavaScript, Python, they're all good examples of these and pretty common. On the other hand, a language like C++ has very compelling performance characteristics. Quite often C#, used as well, sort of as a bit of a middle ground. It's also important to see how, with the language and with the API, how modularizable it is, and how pluggable it is. This affects not only how a game programmer might organize their own code, but it's also a big driver in whether there are any third-party ecosystems that are sort of supporting that game engine that can be leveraged. Engines like Unreal and Unity are really good at this, and they have things like their respective marketplaces to support this, and it's also a source of monetization for them, and also to the users of the engine selling to other users. So users can actually build their own functionality and ship it off to other game users to use. That's pretty cool. Different languages have different levels of debugging support. This can be really critical during development. Often game server engines are distributed systems, so if there's support for debugging across a multi-process kind of system, that would be really useful. These are the sorts of things that you should have a look at when you're evaluating game engine. With the language support, usually the data type that you use to describe the actor data and the payload for the interactions between actors are usually not exactly the same types that you might find in standard libraries for these languages. So generally you'll get the primitives, the ints, the floats, the strings, the blobs, and the integers are usually sized precisely. You'll also see more specialized types like 3D vectors, 2D vectors, matrices, quaternions, that kind of thing. It's usually also collection types available. Usually with the sequence type, usually you might see an associative map, and you probably see something like a set type as well. So collections are interesting from the point of view of synchronization. If you change the element of a collection type, in the ideal case, you only want to send a delta update when you synchronize that changed collection, rather than send the whole thing. This is important for bandwidth, obviously. It's something to watch out for, and you may have to dig through the docs of your game server engines to sort of really figure out whether it does or does not support that. So many game server engines have sort of different APIs that they use on the client side versus the server side, and this kind of makes sense for player-centric models. What you often see with component-centric models is that the client side and the server side are actually the same API. That's got some pretty good benefits. It means that you can reuse a lot of the code that you write for components. So the component that you write for your combat system, for example, that's on the client side, can be reused on the server side. That's pretty neat. It can be a real pain to implement and maintain gameplay features twice. So that's a really good benefit. Can also open doors in terms of allowing server-side AI to sort of simulate player behaviors. So imagine if you had a server-side process that acted like a game client to your simulation. And the parts of your simulation could just be reacted to, just like a player, but controlled by an AI system. So this is useful both in PvE and PvP games. For PvP games, you'll often have a tutorial space or tutorial arena, and you can have bots that sort of guide players through, and they can learn how to play the game without actually hitting human players. This is also useful in terms of load testing. So if you can build AI bots that simulate your players, and they're connecting exactly the same way as a regular player would connect, then you have a really powerful tool to be able to do continuous integration for your game, basically at scale. So that means you can do a lot more systematic and thorough testing of your game. So this is great. what else can you do? You can think about game systems like analytics, space viewers, heat map generation. If we can get some part of the data model out to the server-side process that can take in real-time event streams and do some sort of analysis on them. So really, you're taking bits from the simulation, you're pulling it out, and you're analyzing it in some sort of secondary process. So if you can do that, that would be really cool. So we started off with data model definition. What we've just covered is how a game server engine handles data model manipulation. So I'll talk a little bit about synchronization next. So at the low level, you'll see game server engines use a set of protocols for synchronizing game state. In traditional game servers, UDP was the protocol of choice, and it still kind of is. It's basically a very light layer above the IP protocol. It's unreliable. It's message-based, well, it's packet-based. It means you're not tied to, with TCP, you're sort of tied to the congestion control implementation of the operating system. There's also multiplexing benefits. Being connectionless, multiple connections can talk to a single server-side socket in most operating systems. Often game server engines will implement some sort of reliability layer on top of the UDP, but often they'll have an option to have some parts of it be unreliable. We're seeing a lot more web-based protocols in use for game server engines. So REST APIs are pretty common, as well as WebSocket for more real-time communication. So on top of these protocols, game server engines will implement a synchronization layer for its game state, serializing the game state actors, their data, their interactions across the connection. So typically, after the game state has been manipulated, you need to sort of synchronize that game state to players. So ideally, that would be a delta based on the last state. If single property has changed since the last tick, then only that property value needs to be transmitted in the ideal case. One thing to look at is how frequently game state updates are pushed and which parts of the game state. So in the simple case, the game state is pushed each time it changes to everyone, but in some game designs you might not want this, for bandwidth reasons as well as for gameplay reasons. Often different players will have different views on the game state. For example, in open world games, you'll often want actors that are closer to the player to be updated more frequently than actors that are far away. You might have situations where the game logic determines what parts of the game state update needs to be sent to which players. So for example, in World of Tanks, there's a visibility system. A player might see an enemy tank or might not see an enemy tank because it's behind cover. For anti-cheating reasons, it's actually better not to tell the client about it at all, if you can help it. Because it's very easy for players to have hacked clients that replace assets for camouflage with transparent assets. And so it's better that you just enforce this on the server side to start with. So we can see that there are situations where game logic controls, it might be useful for them to have some level of control over the synchronization of the game state. And it's interesting to evaluate game servers on this basis. We sort of went through that, sorry. So game state is going to be synchronized from where the simulation is being manipulated to other processes. These include clients, certainly, but they can also be server-side processes that host different types of services. So a lot of game server engines have built-in support for metagame services, things like matchmaking, leaderboards, persistence to a database, analytics, account management. So you can think of these services as being sort of dependent on some level of knowledge about the game state, often around the player actor. So in the case of persistence, player data like inventory, appearance, they're useful things to pull out of the game, pull out of the simulation and then sort of store that into a database. Analytics can be useful as well. Basically, if you can get positions out of positions tagged with events from the simulation, you can do things like heat maps, you can do things like analytics for where people die versus what weapons they were using when they died or when they fired a weapon. That kind of level of detail for game designers is sort of used to balance the game design. I mentioned bots earlier as a potential server-side service. it's good to figure out for a game server engine whether you can add your own services as well. So a lot of these matchmaking leaderboards, they're all sort of, a game server engine will often just supply those things for you, especially for those game server engines that are sort of a bit more platform as a service offerings. So this is something that you should be able to evaluate based on the API documentation, for example. This is something that, again, Unreal and Unity do really well because they allow the game developers to write their own services using the synchronization infrastructure that's supplied by the engine. So not only can they use these in their own game, but they can then on-sell these services to other game developers in the marketplace. So we talked about different server-side services in addition to just the simulation. In many game server engines, these services don't run on just one process. And that means multiple processes are going to be involved for reasons of isolation, fault tolerance, and scalability. So an important question to answer is, what are the parts of the server that really need to scale up? If you have more hardware to throw at it, where's it going to go? How much does it scale? What do you get out of it? So many game server engines are offered as platforms, as services, and so this can be hidden away from you. So you don't generally have to worry about it if you're using those services, as long as you're confident that your provider is going to be able to keep up their side of the deal. In other game engines, you're expected to sort of bring and manage your own cloud resources, and so there are questions to answer, like what cloud platforms is supported. AWS is pretty common, but it's not the only thing. What kind of orchestration support exists for the game server engine? How do server-side processes get containerized? How does service discovery work? What kind of automatic scaling support exists? Can this be driven by metrics from gameplay? For example, if you're running arena-based combat games like we are, you'll often want to have some pool of arena servers that are ready for players, but you want that to be moderated by the load statistics that you get from, say, your matchmaking service, for example. So there must be a flexible way to sort of think two things together. As a final point, you might also be interested in evaluating how easy it is to monitor and profile your game while it's in operation. Problems at scale are hard to pick up during development, and so there needs to be some way for game developers to quickly and effectively diagnose those performance issues relating to scalability. So depending on your game server engine, you have different levels of support for that. So bringing it all together, game servers have an idea of the game state, can be defined in terms of actors, data, and interactions that occur in the simulation. We've talked about how game server engines can expose an API for manipulating that game state, different things to look out for that. We've talked about how game server engines synchronize that game state to clients, and not just to clients, to server-side processes as well that might be doing some sort of processing on them. So I hope you take away from this that it's really important. This idea of looking at game server engines from the point of view of how it represents game state, how it works with it, is probably one of the fundamental things that inform whether to pick option A or option B. So it also, hopefully, if you're building your own game engine, gives you some ideas for things to consider when you're doing that. So that's all. Thank you for listening. Are there any questions? Yes?
Yeah, so you mentioned that in World of Tanks, you might not show another tank unless that player has seen it.
Yeah.
And you check that on the server.
Yeah.
So how do you check that? Like, is there like a line of checks?
Yep. So on the server, what that requires is some sort of collision scene to be set up on the server side. So there needs to be some sort of ray test, basically to raycast kind of thing.
Do you do that all the time for every ticket?
I believe so. Yes. Okay. Well, at least it's done. It's done in a way such that when you move, it does sort of a recheck. So yeah.
You're talking about vector-based updating for clients. How do you handle leasing in that situation? Because I've worked on some, you get horrible leasing.
Right. So the question was, how does things like collection types handle desync? So it really depends on. It requires that both sides have that knowledge. So you sort of need two things. You need a reliable channel. So you really need to have things be updates. So partial updates should reference a known state. And a reliable channel should give you that. So things like unreliable channels, you really have to be a bit more careful about that. If both sides sort of know what the state is and one changes, then we can sort of do that. So yeah.